So welcome to my talk. I am Kamalesh and my co-author Tom Hromatka. We both work at Linux kernel team at Oracle Cloud Infrastructure. So the talk is divided into logically three partitions. In the first session, I'll just introduce you to what is Cgroup, and we'll compare and contrast between Cgroup V1 and V2. And in the second session, we'll speak more about what all things you might need to know when you're migrating from Cgroup V1 to Cgroup V2. And I'll introduce you to something known as libcgroup abstractions. And finally, we'll cover touch base on things like interesting feature which Cgroup V2 has, which is called QoS and PCI. Let's have the questions for the last because we have too much to cover. So that's the definition given in the kernel sources. If you open the cgroup.txt, this is the definition of cgroups as such. I'll just give a minute for you, a few seconds for you to just read it. Okay. So now let's see what they really mean by that. Okay. So what I've done is I have a VM with two terminals already set up. And we'll, instead of looking to what is Cgroup and all things, we'll just start with an example of what it means. Is the screen visible to you? I mean, the font size is okay, right? Right. So let's do this. So I'm just going to create two Cgroups. Just say DB and another one called Insights. So if you ask what is CG Create, it's a cool tool provided by libcgroup. And I am the co-maintainer of libcgroup, so I'm more comfortable with this. In another terminal, let's do something known as systemd cgtop. So this is another tool which is provided by systemd. It's a very beautiful tool when it comes to monitoring cgroups, per cgroup things. There's nothing interesting as if now from the directories which we create, cgroups which we created. So let's do one thing. Let's launch some process, say db, let's say stress, CPU 0, and say fn timeout. Oops, sorry, that's fine. Seconds. And similarly, let me launch some process in the other cgroup which I just created. Now, let's go back here. So if you see the cgtop, can you see that it's cut? Is this okay? No, that's still not okay. So if you see the topmost, I don't know why that's a cut. Is this okay? The other one is overlapping. Right? So if you see the topmost two things, right, two cgroups as such we just created, the DB and Insight. If you see the CPU side of things, it's equally sharing the system. So there are 5 tasks in a cgroup, and now if you see both of them are sharing equally. So that's the first part of the definition where they say you can organize tasks into a single hierarchy or a single cgroup. So that's what it meant. Now this is okay. That's this is kind of okay. Now if you want to do is like if you want to give more than 50% of CPU, right? Let's do this, right? What we do is, let's say we want to give 80% of CPU to one particular group. What I can do is, CG set. Sorry. let's not do this. Let's do this way. Now, if you come back to this, can you see that the DB group is getting 80% of the CPU as such, and the inside is just getting 20% of the CPU. So this was the second part of the definition where they meant you can configure the C group the way you want. Right? We'll speak about it, gradually. We'll introduce you more to how the C group and all these things work. For now, just have this in. Let me clear this. Now, that was done. So, when was C group introduced? Some little history behind it. So, C group v1 was introduced in 2.6.24 kernel. It started up with CPU set and CPU controller as such, and gradually with every release, they kept on adding other controllers. And fast forwarding in August 2014, Cgroup v2 was still in development phase, but it was available. If you wanted to mount a Cgroup back then, you would have to use this mount option, which is a down, which says __dev _ sane behavior. So when, by that time, what was available is just the memory controller and the block IO controller is available. And in 2016, with 4.5 kernel, it was declared stable, and you no more needed to add this mount point or any of those things. And gradually what happened was with every release, there were controllers which got added, like RDMA or CPU or PIDs, or all this controller got added then and there. So meanwhile, what happened was in 2009, libcgroup was, if I'm right, it was the only or the first library which allowed or gave you C APIs by which you can manipulate or create, delete, or you can just manage the Cgroup v1 as such. And then the Cgroup support for the libcgroup was added somewhere around May 2021. And currently, libcgroup, can do what systemd does, in the sense we know it can understand slices, scope. We'll speak about all these things later in the slide. And now it has Python bindings too. Similarly, if you see for systemd also, there is a timeline. They supported v1 in 2010, and 2016 there was support for v2, and systemd, I guess the later releases now on would just default to Cgroup v2. We'll speak about this controllers later, but just a kind of introduction to that. So now, what is a hierarchy, right? What's a Cgroup hierarchy? In layman terms or a very simple terms, what we can say is hierarchy is nothing but a mount point. So if you could have seen in your system that all the controllers have to be mounted at one particular point. Everyone would have their own mount point, and they'll be under sysfs Cgroup. So what it means is you remember the demo or the examples which we saw. What I did was I created a Cgroup. I created a Cgroup under CPU controller. So what it means is the CPU controller is mounted in a particular mount point, and similarly a memory control. If you're going to look for memory, it's mounted under the memory controller mount point. So we'll be carrying on the same example throughout the presentation on CPU and memory. So what it means is we created two Cgroups. One is the DB and other is the inside. So, and we launched some process in it, right? And then if you remember, what I did was I gave 80% of CPU to DB alone. So that's how that's just an example of. And similarly for memory, if you want to just give 1 gig of memory, you would just configure it in that manner. It's just a very basic introduction of it, because we have, I'm just touch basing or refreshing it for you guys. And now, what was the staunch or the logical difference which made from Cgroup v1 to v2? It's if you see from the previous slide, the CPU and memory controller were mounted at two different points altogether. With Cgroup v2, what we have is we have something known as the unified hierarchy, where we don't have separate mount points or hierarchy as such. But what you do is you have a single mount point, and you enable and disable controllers per Cgroup. So what happens is if your parent has CPU and memory enabled, the controller is enabled, then the children could enable or disable those controllers or a subset of it. So this is a big logical shift on how it happened, right? And one thing is with Cgroup v1, what you can do is it's not needed that you have to individually mount every controller. It gives you the freedom of mounting one or more controllers together. If you have been using Cgroup v1, you would see is like the CPU and CPU accounting controller or net PRIO and net CLS controller would be mounted together, right? So have this in mind. We'll come back. We'll be keep revisiting the same examples again and again. So this is a simple way. What I've done is like I've laid out, side by side on. If you're using bash commands, how would you create it? What we're trying to create is this previous one, this hierarchy, right, towards the left side. So for that, what are the commands you use, right? If you're going to use in bash, these are the commands you're going to use. And if you're going to use libcgroup, those are the tools you will use to create it. And if you're going to do it by the systemd, that is one way to achieve it in systemd as such. So now the question is like, these are not persistent across reboots. So you have to do it every time. And if you want to make it persistent across, or you want to make the cgroup set a persistence account across the reboots, then what would happen is like bash, you have to create a bash script and then convert that into an systemd service unit or systemd unit and point exe start to it. And for libcgroup, we have an interesting configuration known as cgconfig.conf. It has tons of options available. Just use the man page to it and check it out. It's a beautiful one. And for systemd, you would need to create slice units. Slice unit and the scope units. So this is, how to achieve it, right? If you really want to, create C groups, how would you do it? Now, that logically concludes the first section of, just touch basing with what is C group V1, what is C group, those things. So we're entering the second phase where the things you need to care when you you're moving or migrating from C group V1 to V2, right? So one major thing which I did speak, right, is like it's a multi-hierarchy thing, C group V1. Multi-hierarchy in the sense you can have different controllers mounted at different points. It is not needed that a task which is there in CPU controller should be in the same C group in memory controller also, right? It gave you, amazing flexibility. Then the question comes is like, why did even we move from that kind of flexibility which C group V1 gave, right? So let's consider this example now. We'll take the same example. So, we are on the same page. So now, in the C group V1, you have the DB group, you have some task in it. And then what you do is, you create another C group in memory controller, say not DB, we have another level below it, say DB1 or something like that, and you have task there. And now, what you have done is like for the CPU, what I've given is like, we are given 3 CPUs out of the 4 CPU for the DB group. And similarly, what you're given is you're just given 1 gig RAM. And now, consider that the tasks hits 1 GB limit. What happens then? The reclaim kicks in, and it tries to make some space for you. And by the time, the tasks which are there in the same tasks which are there in the DB group are throttled or waiting for this task to complete. And now, if you're going to be a system admin, this is very painful. You have to track each and every C group for that particular task. That makes it very, that's very, very, painful in doing it. Now, another major thing is like, if you see the C group, if you worked with C group V1, you'll realize that every controller had the freedom of naming it the way it wanted. A CPU controller would say CPU.share. A memory controller would consider it limit to be memory.limits in bytes, right? The naming convention not same across all the controllers. And another point was like the way the input values were accepted. If you take, I can give somewhere around, we'll consider only CPU and memory, right? If you're going to say CPU shares, or CPU shares is nothing but the amount of resource or relatively how much CPU should be allocated to that particular C group kind of a thing. So what it means is like, it can range somewhere from 2 to number of CPUs available in the system. And for memory, the range would be somewhere around any positive number. If you're going to take a 64-bit machine, I guess you can go till 8 petabytes. So you're understanding it, right? So the inputs were not common. Every controller had the freedom to, have their own way of parameters. And similarly for the output also. When you read those settings, you'll find that the values are not common across all the controllers. So that was handled in C group V2. So what would happen is like every controller would have exactly the same names. Like CPU.max, CPU.wait would be there. you would have IO.wait. And for memory, you would have like memory.max and CPU.max. So the naming conventions were same. And the range of inputs are also same. It starts from 1 to 10,000 and default is 100. So these were the things or the pain points which made people to move to, the design decision was taken. And more deeply is like the way the resources are distributed in cgroup v1, v2 was the biggest change, where you have to track different places and if there is a stall or something, the tweaking of the resource, tweaking of the controllers were a little painful. And if you're moving to cgroup v2, there are certain rules or the constraints by which you have to play. The biggest constraint is the top-down constraint, which means my cgroup, right? It has been given 4 CPUs worth of time. It means its child cgroups or its children's should not cross that limit. That's that's in the books, but you can always overcome it. And secondly, you can't have a process running on any of the cgroups. It should be always in the libcgroup. This was one of the major changes. What used to happen in cgroup v1 is, for example, the my cgroup can have its own children cgroups as well as it can have tasks in it. That would mean that the tasks as well as the children tasks are competing for resources, against each other. So that is no more allowed. And they marked or demarked the delegation boundaries very clearly. That was one major thing in cgroup v1. The cgroup v1 was not made for rootless containers or it was not designed in that way. In cgroup v2, we have clear-cut delegation models and what all you should do for rootless containers or those kinds of applications. So another question comes is like you have said that we don't have one-on-one mapping. The naming conventions are different. The input parameters are different. The way the output parameters are available are also completely different. Then how do we migrate, right? So I've just given you a couple of lists where, one-to-one mapping kind of things, it's manageable with these mapping. This is not the complete list at all. So if you see the CPU controller, what happens is like, if you wanted something known as the capping, in the sense, a process should not cross this particular limit or something like that. We used to do it in 2 files. Excuse me. The CFS period, and we'll speak about all this. Just imagine this. So what happens is like it was just made into a single file. And similarly, if you see for CPU set controller at the end, right? In cgroup v1, if you want to do a soft partitioning of the system, you would just use that one particular file where you would say these CPUs are exclusively available for this particular cgroup as such. But in cgroup v2, you have to do it in 2 different files where you even have to specify what kind of partition do you want. There are different kinds of partitions you can have. And now, before we go into libcgroup abstractions as such, if you're using the latest kernels from 6.11 or 6.12, by default, the memory and the CPU set controllers are not enabled. By default, they're not available. You have to enable these kernel configs for them, to be available. So let's try this. Like I said, right, you're just familiar, consider this. You're just familiar with cgroup v1 and you don't know the settings in cgroup v2 and you don't want to take that headache. So libcgroups provide something known as abstraction. It doesn't cover every setting, but it does a very decent job. So what you can do is, let's do this. Don't worry about the demos. At the backup slides, I have mentioned exact commands I'm using. You can go back and look at those commands as such. So what I'm trying to do is, I guess everyone is familiar with cgroup weights now. I've spoken so much about that. So what you're trying to do is you're just trying to get the value of this particular parameter of this controller for group. It says, like we gave, right? It's 300. It's like 3 CPUs worth of time. Now, this is, okay. This is a nice command which ccat provides. It's -m, which says what is the current cgroup mode you have booted in. whether it's Cgroup V2 or Cgroup V1 or it's hybrid. And now, like I said, you're right, we'll do the reverse. Say, I'm not aware of what is in the Cgroup V1. I don't know what is the setting I have to use. So what you can do is like cgx set -1, hyphen, yeah, -1, and you say cpu dot shares, say something like half a CPU worth, and you say for db. You're getting the translation, right? So what you can do is with libcgroup abstraction is like, if you just know Cgroup V2 or you are famous, very familiar with Cgroup V1, you can do the mismatch. I mean, you can just use the -1 or -2. -2 is for Cgroup V2 and -1 is for Cgroup V1, and you can just type in whatever controller your settings you want to set. So libcgroup abstraction helps here a lot. It's still there. We are still adding more mapping. So this is one tool which might help you to migrate. Oh, yeah, we did this. And am I on time? Yeah. So like I said, right, Cgroup V2 comes with interesting features. I would like to present two features here. One is the QoS, which provides you very fine granularity of controlling. I called it as the noisy neighbor problem. Like if you remember the demo first, right? What we did was we didn't do any configuration. What we did was we just created two C groups, and we had 5 tasks spawned in both of them. Both of them, trying to get its share of CPU, and both of them were given 50%, right? This is fine, but think about constraints which you'll have. Say that you need a C group, which you want to limit it to one exact limit, even if there is resource available you don't want it to cross. Those kinds of noisy neighbor problems can be handled in Cgroup V2 very interestingly. Let's take the example of memory, right? So if you see, it provides with these kinds of, it provides you like 4 files. One is called the memory.min. The memory.min, whatever value you put in there, right, that's like a guarantee for you. Kernel will make sure that you get that limit, right? And even if there is reclaim which kicks in a moderate pressure, it's not going to reclaim that memory. It's going to give you, that exact amount you put there. But the caution is like, if the system is like going to stall now, then it's going to reclaim it. It's very rare which happens. And the second one is the memory.low interface. What does that provide? So it gives you kind of a soft guarantee or the soft limit guarantees, which says that, say some GB you put in, it says that the kernel will try to keep up with the promise of giving you that soft guarantee, saying that it will try to give you that number of memory for that particular task in that CPU, C groups as such. And if there is like very severe pressure, it will come down to mem.min. And the third interface is going to be memory.high, which is kind of upper bound of soft guarantees, which says that the moment you hit that particular value, the throttling starts. So that it starts throttling and keeps you in the limit, and there are no oom or any of those things which would happen. And the last one is memory.max. So that, as the name says, that's the maximum you can hit. You go more than that, the oom kicks in, it tries to kill the process because it's not behaving in the right way. And like we saw for the CPU, right? CPU weight is nothing but its relative thing. From the first example where you saw that, like I said, we converted the DB group where we gave 80% CPU, right? So what would that mean is like, out of 4 CPUs, you're giving it 3 CPUs. So those kinds of things is relative. You're saying this particular task relative to this another C group, how much of CPU can you allocate? The resource distribution, right? And next comes CPU max. It's exactly similar to memory max, which says that it's the hard ceiling or the hard limit. Once you hit it, the process is going to get throttled. for n number of seconds or whatever time you're given. And it's a similar for I/O too. Let's do one thing. Let's combine all these things into the one at the last. Imagine that you're creating a C group. What you're trying to say is like, at the minimum, the task in the C group should get at least 1 GB, right? And it'll be nice to have 1.5 GB. I would really like to have it. So that is the memory.low. And memory.high, you're saying, 2 GB is good to have. The moment it hits more than 2 GB, the throttling starts. It'll try to bring the memory back to mem.high. And if it crosses the memory max value, that's 2.5 gig, the task starts getting kicked, and the severe active reclaim kicks in as such. And like I explained, CPU weight, you're giving 3 CPUs, and CPU max, what you're trying to say is, for 1 second, allow it to run only 80 seconds. 80% of 1 second. So effectively, instead of 3 CPUs, what you're giving is 2.2. So, and lastly, similar for the I/O weight and I/O max, which would control the bandwidth as well as the how much of ops you can do, read-write ops you can do, right? So what it provides you is like you can define the whole system or partition the whole system into different C groups. You can put task, you can put in tasks which you think, it should get only this much, housekeeping task or something like that, those things. And you can have the system for other major workload, giving it the max of the system, right? And instead of speaking about PSI, right, let's have a demo of it. It's very interesting to, it's a very interesting thing. So what PSI stands for is the pressure stall information. What it gives you, sorry. So what it gives you is like, per C group, we'll speak about per C group first. What it gives you is like, what is happening with that particular group when the tasks are just stalled or they're waiting on something, right? And it can even give you the whole system-wide information too. No, we'll just go with the demo so it's easier for you to understand. So let's do this. I'm again creating a group, and let's launch some stress here also. Sorry, that's my. Sorry. So now, let's do this. So this is what you're trying to see is like the memory pressure for that particular C group. So if you see the first one, right, what it says is sum. It means that not all the tasks, but some of the tasks are stalling. And for last average of 10 seconds, this is the percentage of stall which has happened. And next column speaks about at the last 60 seconds, what is the stall happened. And the last one would be over the last 5 minutes. That's the 300-second thing. And the second row as such, it shows that, it usually shows, it's like for all the tasks which, there is no progress which is made in the particular C group, and all the tasks are stalled. So that's the information it gives, right? It's super cool thing. And you can you can measure or monitor for CPU pressure and you can check for memory, you can check for I/O, or you can check for the whole of the C group, or you can check for the whole of the system. It's just the interface files you have to read. This is memory.pressure, which I'm reading right from. Now, as an admin, what you can do is like there are two options you have. Either you can kill some tasks, right? Or what you can do is you can just freeze that whole C group. To freeze the C group, what you can do is set -r C group dot freeze equal to 1 inside. So now, if you're going to launch it again, you'll gradually see that all the tasks in that particular C group is frozen, like freeze, right? So that's something you can do as an admin. Or else, let's unfreeze it. And I have this program which I have taken from the kernel documentation so that you can go back and refer. So what you can do is you can register. What you can do is like you can open the memory.pressure per C group or for the whole system pressure, and you can monitor it. So what you can do is something like this. You can see this, right? So what this does is like whenever the memory pressure gets triggered for that particular C group, you start getting, the alert saying that, the event alert, starts up. So this is PCI for you, C group PCI. So that will be all. So I'm open for the questions.
So if a process has more than one use case, can C group be used to tune the parameters per use case of that process?
Process in the sense, a task or process can be only part of one particular C group as such, right?
No, that's true.
Yeah.
A process in different runs, it can run different use cases. Maybe take the example of camera. In one case, it runs as a for preview, next snapshot, or video recording. But the process is same. So in that case, can C group be used to tune differently?
One way to achieve would be is like have two different C groups and have different values given to both of them. And depending upon the use case, you can just keep migrating the task from, say 80% resource C group or 20% resource C group, something that you can do. But you can just have only one task.
But in a single run, I think there is no reboot. The
No,
process.
it's a single run, right? For example, you know that this time it's going to use 20%. You can always migrate it to one particular C group where you're given just 20% of memory or 20% of CPU. And you can have another C group which is created, which can be idle without any task, where you can give 80% of the system resource. And depending upon the need, it can keep, ping-ponging between both these C groups as such. That would be one way to achieve it.
Anyone else?
So assume freezing a C group dials down the CPU time for processes in the C group to 0. What happens to the memory allocated? Do you
Further allocation doesn't happen. It's just there.
just CPU? Okay.
No, not just CPU. What I meant is for memory, the further allocations or anything,
Further allocation
it's just frozen.
And CPU as well.
Yes, all the resource which
And, everything that's been previously allocated stays in memory as is.
yes, because you can always unfreeze it. That's what we did, right?
Right. Yeah. Thanks.
If that'll be all, thank you so much for coming.